In this video, we are going to have a look at inference on correlation and regression. It is important to understand that this video assumes prior knowledge with regards to how to compute the Pearson correlation coefficient and obtain the least squares regression equation from a simple linear regression, right? So it is assumed that you know how to do these things before we move on. And in fact, I already have a video that I've given you on Google Classroom for that. So ensure that you go through this because I won't be able to go in that video again on how to compute correlation, what correlation is, and what regression is, and so on. So we are assuming here that you already know these, and I would request you to go through the first video that I cover in the first semester with regards to correlation and regression as well. Okay. Now, so what are we going to do here? We are going to talk about, first of all, inference on correlation. All right. When we talk about on correlation, I just want to remind you that we are using this data of claim and payment amount. And you had this data that we were working on in the first semester in class. So you will see that there is a positive linear relationship between payment and on settlement and claim amount. Now that is based on 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 observations. Obviously, these 10 observations are assumed to be from a random sample of policyholders where you have their claim amount and the payment amount by the insurance. So it is important to understand that this is a random sample. That's good. But the question that we need to ask ourselves is that behavior that we are observing in the random sample something that we can generalize to a larger population? In other words, if I'm saying that there is a positive linear relationship that is relatively strong here, can I sort of generalize that behavior to a general context? Okay, that is the most important part here. This is why we are going to go a little bit beyond of what we have done last time. Last time in the class, we have just learned how to compute, excuse me, we have learned how to compute the correlation coefficient. And let's suppose you got a value of zero point 0.8 or zero point 0.9, things like that. You would see that there's a strong positive linear relationship, etc., etc. But in our class here, we are not going to focus on how to compute this, as I said to you, but we are going to focus on what would be the correlation coefficient, excuse me, um, what would be the correlation coefficient what would be the correlation coefficient in the population. So you have a correlation coefficient that you're computing using small letter r, but you have a correlation coefficient in the population. That is, let's suppose you wanted to take into account all the policyholders that you have in that data, not in that data, in that company, for example, and you were to plot all of these. Would you have got something similar to what you have in the dark points? Or if you were to plot the whole thing, would you have got something like that, for example? Something like that means what? It means that there is no linear relationship. So if in the population there is no linear relationship, and in this sample you are observing a linear relationship, you might have to be very careful here in terms of your interpretation and not generalize that interpretation, because that interpretation will not normally be significant. So that's important to understand. So what are we going to do? We want to evaluate in the population whether our correlation coefficient is equal to zero or not equal to zero, for example. So here, when I talk about correlation coefficient in the population, you will see that I'm not writing letter P, but I'm using a symbol called rho, RHO, a Greek letter called rho, and rho is used to define the correlation coefficient in the population. And that's what I want to do now. I want to test whether the correlation coefficient in the population, this is my first hypothesis, is equal to zero, or if the correlation coefficient in the population is not equal to zero, for example. So if it is not equal to zero, then you may allow yourself to generalize that information here. But if the correlation coefficient is equal to 0, then it means that this value of zero point 0.8 or zero point 0.9 or whatever it is insignificant. 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 But if it is uh, something like zero, sorry, if it is something like rho is not equal to zero, if your test of hypothesis conclude that it is not equal to zero, then obviously you can say that the correlation coefficient of zero point 0.8 is significant, statistically significant. It all depends. And that's what we want to do now. And for that purpose, I just want to remind you how to compute the correlation coefficient. The correlation coefficient is obtained by taking the sum of squares of xy divided by the root of the sum of squares of x, sum of squares of y. Okay, sum of squares of x, sum of squares of y. And the sum of squares of x is what you see in the numerator here. The sum of squares of xy is what you see here. And the sum of squares of y is what you see here. Okay. So if you want to compute the correlation coefficient, that's basically what you do. But here, for the purpose of inference, what we are going to do is we want to do the following. We want to test for rho equal to 0 and the alternative is rho not equal to 0 if you are looking at whether these are significant or not. Okay. So the best approach to explain to you the inference is to take the question and do it together with you. All right. So maybe what I will do is to open a Word file, and from there I'll be able to discuss with you this inference. Let's take this example here. To start with, your question is there a significant correlation between claim and payment amount? As soon as you see this word significant, that should trigger the response as a hypothesis testing. Whenever this word significant is mentioned, obviously, you are referring to an hypothesis testing that you have to do on the correlation coefficient. If I ask you to compute the correlation coefficient, you just compute it. But if I ask you, is there a significant correlation, you need to check whether that correlation coefficient that you have computed based on the first semester is significant or not. And for that, you will need to run the hypothesis testing on rho equal to 0 versus rho is not equal to 0. Is there a positive significant linear, is there a significant positive correlation between, if this is a question, is there a significant positive correlation, then you will not be testing the alternative as not equal to, but the alternative will be greater than 0. If you are testing for rho, is there a significant negative linear relationship, then you would be testing for the alternative to be 0. But the null in our example is always uh, equal. Okay. Now, getting back to what I was doing here, let me go back to this question here. So, how are we going to proceed? We start by defining our correlation coefficient in the population. So let's get there. So if you have a question like that in exam, that's normally how you would go ahead and do that. Okay. Let's notice such that rho equal to 0 versus h1 is such that rho is not equal to 0. Is not equal to 0. Okay. Now, listen to me. What we need to be careful about here is the first step is to define that rho. let rho be the true correlation coefficient between claim and payment amount. That's normally what you would go ahead to do. In a question, when you have hypothesis testing, you will need to start by defining your row, your terms, and then you're going to state the hypothesis. Why is it equal to and why is it not equal to zero? If it is equal to zero, what does this mean? It means that there is no significant linear relationship between payment and claim because uh, normally a correlation of zero implies that there is no linear relationship. So if the correlation in the population equal to zero, it means that in the population there is no linear relationship. And if in the population there is no linear relationship, obviously the correlation that you have computed in the sample, let's suppose it is zero point 0.4 or whatever value it could be, that value is going to be insignificant. All right, it's actually insignificant. And you can't generalize that. That's what I was mentioning earlier. However, if it is not equal to zero, then it's normally going to it means that there is a significant linear relationship. All right, that's the basic idea. So generally, we aim for that. When this is done, we are going to state what type of test has been carried out. A two tail tailed test is carried out at the 5% level of significance. This is what I mentioned here, okay? Now, then under H note, you will say it's a bit the same kind of thing that you do for all kind of hypothesis testing. Under this null hypothesis, that is for which rho is equal to zero, you are going to state the distribution of your test statistic. What is the distribution of a test statistic here? This is what I explained here. The distribution of a test statistic is that r root of n by 2 divided by 1 minus r squared follows a t distribution. So what does it mean? It means basically that you have your point estimate minus the row under H node. And the row under H node, as you would have realized, is equal to 0. So if the row under H node is equal to 0, then we don't have anything like that. So the next step would be what? To minus 0 divide by the standard error. And the standard error normally in the case of correlation, now I'm skipping the details of why this is the case here. This is not the purpose of our class, but just for information, the standard error is obtained by 1 minus r squared over n minus 2, the square root of this thing, okay? So just like you have a standard error for mu, which is sigma over root of n, you have the same standard error for not standard error for mu, excuse me, standard error for x bar, excuse me, standard error for x bar. In the same vein, you have a standard error for the point estimate r, and the standard error is root of 1 minus r squared over n minus 2. So, but sometimes instead of writing it like this, you would prefer just to write it down as n minus 2 divided by 1 minus r squared. Though I would, if you want, you can just write it as it is here. So sorry, you can write it as it is here, r divided by this. It's the same thing anyway. So that's an alternative way of writing it down. So that follows a t distribution. So let me go back to the concept here. Under H node, we will say that the distribution that we have are the distribution of our test statistics, excuse me, are into the square root of what? N minus 2. The whole thing you divide by square root of 1 minus r squared, as we have seen here, or n minus 2 over root of 1 minus r squared, that follows a t distribution. That follows a t distribution. That follows a t distribution. A t distribution. Now, when we talk about a t distribution, we are of course referring to alpha. A t distribution with a certain value of alpha, and the degree of freedom in the t distribution is going to be n minus 2, right? The degree of freedom is going to be n minus 2. Don't forget, this is the distribution of a test statistic. It's always going to follow a t distribution, the test statistic, in the context of correlation. Again, I'm skipping the mathematical details of why this is the case. This is not the purpose of my class here. It's just applied my class. I'm not getting into the details of why this is following a t distribution and so on. But for your information, all this happens because there are certain assumptions that we are going to set. In a moment, I'm going to explain to you. So remember, we start by the following. We define our term, we state the hypothesis, we are going to state what is the level of significance, and then we decide, we determine under H node what happens, okay? But before we determine under H node, there is one step I forgot here, which is the assumption. Assuming that both x and y means what? Both claim and payment amount come from normal populations. Now, if you have, well, I'm not going to get into that. If you have learned the concept of multivariate normal distribution, you could have said that. But in our case, you will say, assuming that both claim and payment amount come from normal populations, then you will say under H node. It's always good to state your assumption first, then you say under H node, and then when the H node, you state the distribution of a test statistic. The next step, obviously, would be to compute that test statistic. Now, listen to me. I'm going to get back here, and to compute the test statistics, obviously, you should have computed these values in the past semester, and from these values, you would have computed. Let me show you that. From these values, you would have applied this formula that you are seeing here as per last semester. So you would know that you need to take the sum of xy, which is 1980 here, minus sum of x, which is 141, minus multiplied by 131, as you are seeing. And let me go back to that, and then divide by the square root of sum of x squared, which you already have here, 2140, minus sum of x to the square, that is 141.6 to the squared, divided by n represent the number of policyholders in my case, which is 10 in my case, so you will divide by 10. And then the same thing for sum of y squared, where you have an 1843 divided by, minus sum of y to the squared minus 131 to the squared, divide by n again, and then you take the square root. That's what you would have had to do, but for the purpose of, for the sake of time, I'm not going to get into the computation again, but I will just compute it directly from Excel, and the value is 0.958. That's what we would have been computing last semester, 0.95824. So then, based on this value of R, we are going to replace that in our formula here. So we'll say that T equal to, because our computed T is equal to 0.95824, 0.95824. Then you will take the square root of 10 minus 2, as you recall that n is a sample size here, which is 2, and then the whole thing you divide by square root of 1 minus r squared, 1 minus the value here to the squared. And then What you need to do is to say it is equal to, and then you will get the value that you are looking for. Just give me a second with you. So the value that you have is supposed to be 9.48, 9.478. So the 9.478. Okay, that's the value of t. Now the next step is we need to state the rejection region. If, remember these steps, if modulus t, in my context I would say modulus y because I'm running a two-tail test. If I was running only single tail test with one tail test with greater than, then I would say t is greater than. But given that I'm doing a two-tail test, it means that t could be greater than the positive value of something that I need to find, or t is less than the negative value of something that I need to find. Now, if t is greater than what? That is a critical value. We reject. We reject what? We reject h. We reject h. Note. If t is greater than what? What value? So we have our distribution. I'm just going to draw it somewhere here. Uh, so, well, let me go there. So we have our distribution, which is a t distribution, and we are asked to find this. I'm not discussing what the t distribution is because we already discussed that in previous lectures. So I will have to find the critical value that correspond to 5% level of significance. So 5% level of significance, because it is to tail, means that on this side you are dealing with 0.025 as an area, and this is 0.025 as an area, where these two shaded parts represent the rejection region. And you basically need to find this value that correspond to that critical value here. And this critical value, you can obtain it from the t distribution that I've given you in Google Classroom. So the t distribution is what you are seeing here. And we just need to look at the 0.025 on the right and 0.025 on the left. So the Q correspond to 0.025, the area of Q correspond to 0.025 because we are doing it 5%. So it's divided into two parts, one on the left, one on the right. So that's why it is not zero point 0.5 but 0.025. So you look for Q 0.025, and that's the column that you have to look for your critical value. Under that column, you'll get your critical value. Now, the question is, uh, how do you get that value? It is based on the degree of freedom. And for us, the degree of freedom is n minus 2. What is n? N for us is 10, if you would recall earlier. So 10 minus 2 means 8. You need to go and look for 8. 8 is here, 2.306040.025. So the answer is 2.3060. So in other words, what is happening here is that this critical value that we were referring to is 2.3060. This is 2.3060. 2.3060. So that is the critical value. This is, of course, the negative value of 20.0. Now, we just need to include this information in here. If modulus t is greater than 2.3060, we reject H node. Just bear in mind that if you are doing modulus t is greater than 2.360, greater than 2.3060, is the same as saying if t is less than negative 2.3060, or t is greater than 2.3060, we reject H node. But mathematically, rather than writing this lengthy step here, you could just put modulus t. It's the same thing. Okay, we are just writing a short notation to describe that. So if modulus t is greater than that, we reject h naught. Now, since our modulus t that we have computed is equal to 9.478, if this value was negative, you would say modulus t is equal to 9.4, not the negative. You will put it as positive. And this value, obviously, it goes according to that rejection region because 9.4 is definitely greater than 2.306, so we reject. So in that case, if it was, let's suppose, 1 point something, it does not go according to that, then it would be less than. But now we can text it is greater than, so we are saying that it is greater than 2.3060. We reject, since this, we reject the null hypothesis. We reject H naught if you want at the 5% level of significance and conclude that. Now, what is the conclusion? Given that it is greater than 2.306, we have rejected the null. If we reject the null, what does it mean? It means that this is not holding true. In other words, we are saying that rho in the population is not equal to zero. In other words, we are saying that this correlation of 0.95824 that we have computed is indeed significant, and conclude that the correlation coefficient between claim and payment amount is significant. All right. Remember that that was the question that we asked. Is there a significant correlation? So we have concluded that there is a significant correlation. Now I will do the same thing now for I will do the same thing now for regression. And when I will complete the regression step, I will get into the how to do all these in R. So, but bear in mind something. I just want to go back through that quickly. When you are answering a question on hypothesis testing in correlation, here you need to ensure that you define your rho, you state your hypothesis, you state what level of significance or whether you are carrying out a tutorial or whatever it is. You put down your assumptions, and the assumptions are that the two variables x and y are normally distributed from in the population. And then you will see that under H note, following the assumption, you will see that under H note, this test statistic follows. All right. We have a t distribution for that particular test statistic. And then you compute the test statistic. Obviously, we are going to call it capital T because it follows the t distribution. And then we state our rejection region. I explained to you how to compute and obtain this rejection region. It all depends on how your area is divided, whether it is divided into two or only one-sided. Then you will be able to know what value of Q you need to use in your statistical table, and then you give your conclusion in the plain English, which is this, in technical terms, sorry, which is this: since modulus t is greater than, we reject the null at 5% level of significance, etc. And then we give the English conclusion, the plain English conclusion, simple conclusion, and conclude that the correlation coefficient is significant. So that's the way you answer a question on correlation coefficient. Now, the same thing I'm going to do for regression now, okay? It's important that you understand how to do these manually. Why? Because when I'm going to get into the computational part in R, things will get a little bit easier. So let's move directly on inference on regression coefficient. So we have correlation, we have regression, and now what are we going to do? Let's have a look at the question that was given to you. Just to make things a little bit easier, We will get directly into the question and then we will continue. So our regression here, uh, before I get into the question rather, I just want to explain to you quickly. In the regression coefficient, when you're obtaining the least squared regression equation, you have your y cap, you have your y cap is equal to a plus bx. Now, we are generally not interested that much in this intercept as much as we are interested in the regression coefficient here. Now, this regression coefficient is what is of interest to us normally. Why? Because if this b equal to 0 in the sample, that would mean that our line is like that in the sample, indicating that our point revolve around this line and there is no linear relationship. There is no relationship between payment and claim. But in my context, this is not the case. We observe that b is equal to 0.88 to 3, right? You see that b is equal to 0.8823, which is a positive value. It is not equal to 0 in the sample. So that's good. So in other words, we are stating that when claim amount is increasing, on the other side, payment on settlement is increasing as well. But what matters is, again, as I just explained to you earlier, it's not that simple that matters as much as what is the situation in the population. So our aim, just like we tested for rho, now we are going to test for beta, right? Beta representing the true regression coefficient in the population. I repeat, just like I explained to you in correlation. If this is what you have in the sample of 10, if you take all the population of policyholders and you put them right there as a scatter point, and then you try to obtain a regression coefficient in the population, that will not be called B, but will call beta because it is a general one. And if you get something like what I've just showed you, in other words, it would mean that beta is equal to 0 in the population. Otherwise, if it is not equal to 0, farewell, okay? If it is not equal to 0, then it means that there is a linear relationship. So that's the kind of thing that we want to do, is we want to test in the population whether the regression coefficient that we have obtained here is significant or not. The same kind of idea that we have gone through in correlation, okay? So, because if you have computed 0.882 showing that there is a positive linear relationship in the sample, if you say that this is the same thing in the population and beta is equal to 0 in the population, that would not make sense. So you need to ensure that whatever you have computed here is coherent with regards to what we have in the population. So this is why you need to do an hypothesis testing on beta equal to 0 versus beta not equal to 0, or less than 0 or greater than 0, as um, I explained to you earlier. Now, how would you know if it is greater than 0 or less than 0 or not equal to 0 as the alternative? Very simple. Let me give you an example. Is there a significant linear relationship? If I say there is a significant linear relationship, I did not precise whether it is positive or negative. Then obviously you will use this alternative hypothesis. Is there a significant positive linear relationship? If I say is there a significant positive linear relationship, then you will be using beta is greater than 0 as the alternative. Otherwise, it would be less than 0. That's the kind of thing that you will have to do. Now, so what are we going to get into now is to go, excuse me, I'll discuss that, doesn't matter, but I'll open it again. We'll get into that question here and we will try to answer that together just like I did in Is there a significant linear relationship? Look at the question. In correlation, we don't say is there a significant linear relationship. We say is there a significant correlation, all right? But here we are saying is there a significant linear relationship. So we have we don't use correlation to answer that, though if you wanted to use it, it would really lead to the same conclusion. But the right way of doing it is to test the slope parameter. Now, to be able to do that, let's have a look at an example and then we'll go through that example and do the testing, all right? We'll go back to the same example that we've been working earlier with the claim and payment amount, and we'll get into that. So to start with, just like in correlation where you define your term, I just explained to you that for us the term is going to be beta. So what are we going to do? Let me just copy that and put that down there. I will say let beta, excuse me, be the true slope parameter between claim and payment amount. I repeat, our aim is to know whether beta in the population is equal to zero or not. Okay, if in the population is equal to zero, but here you have a positive linear relationship like 0.88, then that value has to be taken with caution. All right, normally you would not want to generalize such result in the population. You would rather stick to your sample and do your conclusion only on your sample. All right, but uh, if you are testing beta is equal to zero and uh, you got beta not equal to zero, then it's okay. You may say that this regression coefficient is significant. All right. So let me go back to this. So let beta be the true slope parameter between claim and payment amount. Then in the next thing that you need to include here is that H note is such that beta is equal to zero versus beta is not equal to zero. Why? Because I want to know, is there a significant linear relationship? Because that was the question earlier. Is there a significant linear relationship? I did not say is there a significant positive linear relationship. I said, is there a significant linear relationship? So for that particular purpose, that's why I say it is not equal to zero. If I said is there a significant positive linear relationship, that would have been greater than zero. Okay. Now this is done. We need to go for the same step. A two-tailed test is carried out at the 5% level of significance. That doesn't change. And then you need to do your assumption. Now, when we come to the assumption here, you will normally, let me just write this down. When you come to the assumption here, you will normally assume that B comes from a normal population. What is B? B is the regression coefficient that you have computed here. What you have computed last semester. Let me just remind you about that. A B is the sum of squares of xy over the sum of squares of x. All right, just as a kind reminder, the sum of the squares of xy is the sum of xy minus the sum of x, sum of y divided by n, and the whole thing you divide by the sum of x squared, which is the sum of x squared minus sum of x to the squared. Excuse me, let me write this down properly, minus sum of x to the square divided by n. So that is how you obtain b. All right, so you will normally apply these formula on that here data where you have sum of xy, sum of x squared. You will use this, you will use this, you will use this, and use this to compute your b value. And as I said to you, the intercept is not really of relevance normally, so you will rather focus on b. Right. So let me go back to what I was doing, assuming that B comes from a normal population. Now, why do we say that B comes from a normal population? Because you have to bear in mind that this regression coefficient that you've got here is one among many others. Let's suppose if you were to take another sample, you would not expect to get 0.88 to 3. You might have got negative, even a negative value. You might have got a zero 0.2. You might have got all kind of values that you can imagine of. So, in other words, if v data was to change each time, you would obtain different regression coefficients several times. So, and each of these regression coefficients that you would obtain would come from a normal population normally. So our assumption here is that if you were to take this b as 1, and you take another b which is zero point 0.7, another b which is negative zero point 0.8, another b, etc., etc., etc. If you were to repeat that sampling procedure several times, rather having only 10 individuals, you take several 10 individuals each time and you compute the b's. If this was a possibility, if this was the case, then you would have assumed that the b comes from a normal population. That's the idea behind that. Okay, assuming that b comes from a normal population, again we will write down under H node. This is the usual. Under H node, we need to write down this distribution of our test statistic. Now, the distribution of our test statistics is what? So let me go there. When it comes to the distribution of a test statistic, obviously it will be the value of b, just like r minus beta, but under H node beta is equal to 0. So we have to divide by the standard error of b. Now, what is the standard error of b? Standard error of b is what? The standard error of b is going to be, let me write it down like there, the sum of um, the standard error of the standard error of the residuals over the sum of, divided by the root of the sum of squares of x. That's what it is. Now, I will explain to you what all this is about. So, you see there is a difference between this point and this line. You see the vertical distance each time between the point and the line. These vertical distance represent the residuals, all right, the error terms. Now, what are we talking about when we talk about some of the SE, this small SE? SE represent the standard error of the residuals. Now, the estimated standard error of the residuals. And now, the estimated standard error of the residuals is obtained by taking the sum of squares of y minus the sum of squares of xy to the square divided by the sum of squares of x, divide the whole thing by n minus 2. So that is how you obtain the sum of, it's not the standard error that you get, but rather the variance of the error term, right? The variance of the error term can be computed through that formula. Now, note something. This squared is not for the whole thing, no. The squared applies only to the numerator here. The denominator is still sum of squares of x. Be very careful about that, please. So now when I talk about this is sum of squares, this is the variance of the error terms. The variance of the error term means that if you were to take the vertical distance each time and then calculate the variance divided by n minus 1 or something like that, or the variance simply, you will get this value. But it is not straightforward to go and compute each point difference between the line and so on. That is very tricky and complicated. That's why we have a closed form solution for that, which is here as you are seeing. Okay, so we might want to use that formula to be able to obtain our sum of squares, not sum of squares, but the standard error for the residuals. So let me go back to what I was doing. Yes, I was saying that V regression. That's what I explained here, by the way. So that's what I'm showing you here, divided by n minus 2. And this is, okay. And you will see again the test statistic here is B divided by the error term, standard error divided by the root of the sum of squares of x, and the rest is more or less the yeah we so sorry, I'm just not showing you the screen, but let me just find that out for you. So as you will see here, it's the same thing that I just explained to you earlier. So now you will see that distribution is the same t distribution, But now I'm going to continue with what I was doing. So assuming that B comes from a normal population, the H node, and the H node what? I already explained to you, it is going to be B divided by S E. There we go. And this is what we have. Assuming that B comes from a normal population, our test statistics, which is obtained by the point estimate, subtract the beta, but beta under H node is equal to 0. That's why I'm not writing it. Divided by the standard error of B. The standard error of B is the standard error of the residuals divided by the sum of squares of X, as you are seeing. So our next step, this follows same thing, t distribution, same like what you have done in correlation. There is a very strong similarity between these two results. So by the way, so let me compute the t. The t is obtained by taking b. I can compute it, but rather I will do something else. Let me show you how you can draw that in. Uh, how you can obtain that quickly. You can draw a scatter diagram as you're seeing, and then here you right click on any of these points, you add trend line. When you add trend line, you will see that there is linear, etc. You keep it as linear, and then you say display this equation on chart, and you can display R squared as well if you want to compute to check the coefficient of determination later. So our aim here is to get this 0.8823 in this equation here. 0.8823. Yes. And where was I? 0.8823, and the whole thing you divide by the sum, the residual standard error. Now the residual standard error, as I explained to you, we will take the sum of squares. Let me just first of all start by the variance. It's going to be the sum of squares of x. So we have to compute it this time. Unfortunately, I don't have the information with me, but we will have to compute it, okay? I'm going to compute the sum of squares of xy. This is equal to this sum of squares of xy. You can follow where I'm clicking, please, just to ensure that we don't take too long. So sum of squares of xy is equal to sum of xy minus divide by 10. So what are we doing here? We are taking the sum of squares of xy minus the sum of x times sum of y. And the whole thing you divide by 10. That's done. We are going to do the same thing now for sum of squares of x. Which is the sum of x squared minus the sum of x to the squared divided by 10. So this is done. I also need the sum of squares of y. sum of y squared minus sum of y to the square divided by 10. Here we go. Now, if you want to compute the s squared e, you will need to take the sum of y, sum of squares of y, minus the sum of x, sum of squares of x, y, sorry, to the squared divided by the sum of squares of x. And the whole thing you divide by 8, 10 minus 2 gives you 1.17. Okay. Now our next step is to go back here, is to obtain that, as I said, to 1.17. 1.171 is sum of squares, the sum of the sum but the standard error of the residuals. So what are we going to do? We are going to take the root of that thing divided by, so let's take the root all at one go. So 1.171 divided by the sum of squares of xy, sum of squares of x, sorry, 135 plus 0.104. And this is equal to 9.478. 9.477 this time. Now listen to that. You will see something interesting here. In fact, you will see that the results for these two are very similar, and that's what you expect if this was the case in an exam setting where you have only single data. We are asked to do these two things, then you can use the information that's already computed there. That's one thing. Okay. Now, what are we going to do? We are going to repeat the same thing, and there's no need for me because we are talking about the same degree of freedom, because it is n minus 2, the same degree of freedom, and here we are taking the same thing. Then I can just repeat the conclusion there. Since t is equal to this, we reject the null hypothesis and conclude that there is a significant linear relationship. Significant linear relationship between claim and payment amount. That's what you would conclude. Since this is greater than, we reject the null with 5% of significance and conclude that there is a significant linear relationship between claim and payment amount. So that's a little bit how you get to do a question hypothesis testing for regression correlation. You basically just need to know the steps, and that's basically all you have to do. Our next step now is to do the same thing, but on using R. We will open R and we are going to input the data. So You will observe here, I've already put the data myself somewhere. So I'm just going to paste that here to make things easy. So here what I'm doing is that I'm defining claim as a vector containing the different values. We can just give a quick check with these values. You see 8.4, 9.6, 10, 12.8, 14.4, 15.2, 16.4, 16.8, 18, and 20. And we just check the other one as well, 8.72, just to ensure that we are not doing something wrong. There we go. We got all these different values already set up. Now, what are we going to do? We have just input these values as you are seeing. And then to make things a little bit easy, what we are going to do, we can compute these different sum of squares that we have computed already there. Okay, with sum of squares. I'm not going to do it for all. I'm just going to show you for one. Okay, but in any case, let me give it a try and let me do it because I want to show you um, how we obtain these values and how we get the same thing directly from an output. So first of all, I will compute the sum of squares of x, y, sum of squares of x, sum of squares of y, and so on. So let me do that quickly. And so if you want the sum of squares of x, I can call it sum of squares of x like this. And we can just cross check if we get the same value. That's the same value here, for example, 135 point. How are we going to do that? So we will need to take the sum of x squared, as we know, the sum of x squared, that is that sum of 2140. How do we get the sum of x squared? It's what is x? In my case, x is claim and y is settlement. As you would recall, x is claim, y is settlement. Why? Because the settlement payment amount depends on the claim that has been made. So that's why x is claim and y is payment. So what are we going to do? We will do sum of claim to the squared. That's the first thing, minus the sum of x to the square. Very often, student, by the way, this is a big issue that I have very often over years. Where let me just go back to there, where students confuse the sum of x squared with the sum of x to the squared. We are not saying the same thing here. Sum of x squared means that you need to take 8.4 to the squared, 9.6 to the squared, etc. And then you sum. But the sum of x to the squared is you take 8.4 plus 9.6, etc. Then you square. So there's a difference though. Sum of x squared is squaring this. So sorry, sum of x to the squared is squaring that. Sum of x squared is this value that you have obtained after squaring the individual values. So be very careful about that. So we are taking the sum of x, where is this? We are taking the sum of x squared, as you see, claim to the squared, then you sum, minus the sum of claim to the squared, and then you will need to take that value that you have obtained, divide by this last part. You remember sum of x minus sum of x squared. Let me just go back to this slide. Wait. You remember this? Sum of x squared minus sum of x to the squared over n. So I'll need to divide by n. And how do I get to divide by n? To divide by n, I will come here, I will do divide by length of what? Length of claim minus 2. So we are dividing by the length of claim minus 2 as you are seeing. So that's the main thing, not divide by the length of claim, not minus 2, excuse me. I'm doing something wrong now. So length of claim, where is this? There we go, divide by length of claim. Now, when we talk about length of claim is basically just the number of elements that you have in claim, all right? As simple as that, okay? So that's the first step, is that I'm going to take what you are seeing here, the sum of claim to the squared minus the sum of claim to the squared, and that I'm going to divide by the length of claim. That's basically all I need to do here. So I'm going to execute that, and then we can just quickly check the sum of x squared. So sorry, first of all, I need to run all this. And we can just quickly check the sum of squares of x, and we get 135.104. The sum of x squares, 135.104, the same thing. Now, I guess you would have understood that if you have to do for sum of squares of y, it's a quick thing there. I just need to replace that by y, and then I need to replace the claim by the word settlement. So I will just find that and replace by settlement each time. You may write it one by one if you want. So we are going to come here and we are going to do replace. Here we go. That's all. And then we can execute that. And then you can just check the sum of squares of y, and you see that it is 114.541. Same thing. Now we need the same thing now for, so let me just copy that last one. And then this is the sum of squares of xy now. So the sum of the squares of xy is not settlement to the square, but it is the sum of claim times settlement. Sum of xy. Claim times settlement, isn't it? And then minus the sum of not settlement to the squared, but rather the sum of settlement multiplied by the sum of claim. Remember the formula again. This is the formula that I'm referring to. Is that here we go. Sum of x y minus the sum of x times sum of y divided by n. All right. So we can execute that. Let me just check before I run that. So when I do length of settlement, it could be length of settlement, it could be length of claim. It doesn't matter. It's the same thing anyway. Okay. So execute that, and then we check the sum of squares of xy, and you see that it is 119. We can confirm 119 as we have seen here. Now, if you want the residual error variance, the residual error, standard error, like here, the sum of squared e. You remember the sum of squared e? Not the sum of squared e, but SE squared. So if you want the SE squared, you would recall that the SE squared is this formula here. Just quickly, I'll just show you so that you don't get lost. It is this formula that I'm referring to. So you need to take the sum of squares of y minus this and the whole thing divided by n minus 2. That's what I want to compute. That is the residual error variance, right? So let me go back to here. So I come here. This is not necessarily what I'm doing because we already been doing these, all right? But I just want to show you that to confirm what we have done. So to be able to obtain the, I will call it SE2, to obtain that, you would see that we have to take these different components. So it's the sum of squares of y minus the sum of squares of xy to the squared. This thing you divide by the sum of squares of x, right? Remember that thing here. Then the whole thing you divide by the length of whatever, settlement or claim, etc. Length gives you what, by the way? If you are not getting what I mean by length, it's just 10 in my case, all right? Length of claim is 10, length of settlement is 10, it's the same thing, divided by minus 2, all right? So if you want to obtain the residual error variance, that's as simple as this. We can execute that and we can just quickly check what we got as a value, 1.17. So let me just check that again. So 1.17089, 1.17089. You see, as simple as that. Now, if you want the residual standard error, if you want the residual standard error, then you need just to do SE, which is equal to the square root of SE2. All right, and then you will get the residual standard error. So that's a quick check of what you have here. Okay. And this residual standard error is the one that I've been using here. So in the square root here, all right? Now, what I want to do now, next step, is to really apply, to obtain the output directly in R. This was not necessarily everything that I've been doing here, but I just wanted to show you this if ever you want to confirm manually whatever you're going to obtain right now. Okay. Now, the simplest thing to do in doing a regression or a correlation is to do LM. LM, which stands for linear model, and it is a function that is in base R version that enables you to do simple linear regression model, apply simple linear regression model, or multiple linear regression model, but it helps you to apply linear models. So you need to know what is your y and what is your x. Obviously, our y, that is a dependent, is settlement, and is our claim is claim. Our claim is, excuse me, our claim is a deep independent variable. So if you just execute that, you will see that you get an output where you have the intercept and you have the claim. The value of A and you got the value of B, things that you have already been doing in the first semester. All right, we can just confirm these values with our output here. You would see that our B is 0.8823 and B 0.8823, and our intercept, which is not obtained here, which is not required in this output, but which you have done in semester one, is 0.6545. By the way, you can just quickly have a look here. You will see it is 0.6545. That's what we have already done. And you will see that there is coefficient of determination as well that I did not mention. I'm going to explain that in a moment. Bon, let's take that coefficient of determination for the last, right? So that I don't get so that I don't bring any confusion in this work here. I'll stick to what I'm doing. Now, what are we going to do next? Let's go back to our output. Next thing, we are going to do a summary of this LM. This is okay, but it's not that interesting as much as the one that I'm going to show you. The summary of the output now, we are going to give it a name. Let's call it S. Is what is of relevance, and this is what will enable me to know whether I need to whether the regression coefficient is significant or not, whether what I've done here is similar to what I'm going to obtain here. Let me just execute that S, and you can just run the S, and you will see that here we go, we've got the output. Now let me explain to you a little bit these outputs. With output, maybe I will do that while vertically. So let me explain to you this output, okay, what they mean and everything. Now, this output, when you're looking at it, it indicates quite a number of things. To start with, we have a distribution of the residuals. Just a reminder of what the residuals represent is here, the distance between the point and the line. So here we have positive values. Below the line, we have negative values. So that's why you have negative values on this side for the minimum, and you have positive values for the maximum. Now, when it comes to the median is expected to be close to zero, obviously. Otherwise, it would indicate that this distribution of residuals is not totally symmetrical, because the mean, which is not shown here, is normally zero, right? When you're running a regression based on the principle of least squares regression equation that I explained here, we are that I explained in the first semester. However, you need to understand that the mean is expected to be zero. So if the median is not close to zero, then it means that there is a problem somewhere with the model, right? It's not, maybe the model is not appropriate for a linear model is not appropriate. Now, then you have these different estimates. Now, it's very important to understand something is that generally we don't pay too much attention to the estimate that we have here. Now, for your information, you will remember that we have obtained B as 0.8823, we have obtained A as 0.6545. And these are the values that you see reproduced here, 0.8823, 0.6545. This is the estimate that you have for the intercept of A, and the estimate of B. This is the value of B, this is the value of A. Well, the value of B is what you are seeing here for claim, the regression coefficient. And we won't pay too much attention to that one, but we will focus mainly on this part here. This is obtained easily. So in an exam setting or in a question or anywhere, it might happen that I come to you and I hide such information. And then you might have to determine and find ways of determining this value. For example, let's suppose I add this information and everything stays as it is. You should be able to obtain this estimate when you are looking at the standard error and the t-value. Right? When you're looking at the standard error of b and the t-value. Let's take a look at the standard error first of all. You see the 0.09309? How did we get the 0.09309? It's very simple. Let me go back to here. You when we talk about the standard error of B, what does the standard error of B means what? You know that the standard error of B is that full denominator that you see down there. All right, if you take the root of 1.17571 over the sum of squares of x that we explained, that is the standard error of B. So let's suppose now I come back to here where we are, and if you want to find this standard error of B, what do you need to do? It's very simple. I need to take this SE divide by the square root of the sum of squares of x. You remember? Here, I just explained that. Or you can take the root of s squared e divided by the sum of squares of x, the same thing. Or you can take se divided by the root of sum of squares of x. That's what I'm doing. And we have our se computed. We have a square root of sum of squares of x. We compute that. We are expected from that to obtain 0.09309. We execute that and you see that 0.09309. So the standard error is very clear. It's how we obtain it. It's the denominator that you have here. This is the standard error from the t statistic. This is the standard error. Okay, I'm not going to get back into this explanation here. I guess you can rewind and just check. Okay. Now, when you have a t-value, the t-value is what? The t-value is simply this whole thing, the 9.477, that is the 0.8823 divided by the standard error, and that gives you the 9.478 that you are observing here, all right? Of course, because of matter of precision, you won't necessarily get exactly the same thing sometimes, but it's only one small decimal place difference, okay? So here we go. We got the t-value. You understand how to find the t-value. So if you want to, if I come in an exam setting and I hide this information, I guess you should be able to understand how to obtain it. If this information is hidden, you know that this information is obtained by sorry, the t-value is obtained by taking the estimate here, the 0.8823, divided by the standard error. So it's just simple. You just make the estimate the subject of formula to obtain it from these two values. It's like this. Sometimes I can come and hide certain information. Not every This information that I will hide and ask you to find. Normally, they are supposed to be found easily, or somewhere you need to read the question well and find out where you can get this information. There is nothing that I'm going to hide that you can't find normally. All right, you should be able to find these question solution somewhere. And then there is another concept that comes in here, which is the p-value. Now, let me explain to you. I'm not going to get into the full explanation of what the p-value is, the all details of it, but I'm going to get into the basics of what you need to require. In an hypothesis testing, this is for the case of a simple linear regression analysis that we are doing. But for any hypothesis testing that you do, anything, whether you're doing a test of association, whether you are doing whatever test you are doing, whatever analysis you are doing, anything, you will need to understand something is that when we are running an hypothesis testing, you need to check that thing that we call the p-value. That p-value is very important. Because if the p-value is smaller than 0.05, which is your given level of significance, and the p-value is what we call the observed level of significance. All right. If the p-value is the observed level of significance is less than the given level of significance, we will say that we will need to reject the null. That's always the case. I'm going to explain that in a minute, but quickly, If the observed level of significance is lower than the given level of significance, then we reject the null. So generally, we take the significance level as 5%. Most setting we do that, except if in a question it is precisely stated otherwise. But most of the time, it is 5%. So if the observed level of significance is less than 5%, what is the observed level of significance? This value. And this value, you see that it is 0.000 up to four times, and then 127. Obviously, this zero point 0.0 that you are seeing, 0.0000127, this value is logically less than 0.05. 5% means what? 0.05. So if it is less than 0.05, we reject the null. As simple as that. What we do? We reject the null. If this value is less than 0.05, we reject the null. If the value is greater than 0.05, we do not reject the null. That's the same kind of principle that applies in this hypothesis testing or any other hypothesis testing questions that you might have, whether in my class or another class. Whenever the p-value is less than 0.05, we reject the null. In my case, we are rejecting the null. Why we are rejecting the null? Because this value that we call the p-value, p-value, all right, which is also the observed level of significance, observed significance level. This p-value, which is the observed significance level, is less than the given level of significance, so we reject the null. Is it true that we need to reject the null? We can just have a quick look at our result that we have obtained here. So since t is greater than 2.306, we have rejected the null. So you clearly see that based on that, we rejected the null. So just looking at this output, we reject the null. So the p-value is the probability of getting a t-value as extreme as the one observed, assuming that your H naught is true. In other words, what we have just done here is to compute a p-value. We have just have a look at the p-value being equal to probability that the modulus t is greater than or equal to 9.4. And that's what we computed. And this p-value is equal to the zero point 0.0 what you see here. Okay, that's what we just computed, by the way. So the for the two-tailed test, normally as extreme, when I was mentioning as extreme means what? As extreme means very large positive values or very large negative values. All right, just bear that in mind for the case of a to test. That's why I also put the modulus here to explain greater than or equal to 9.477 or less than negative 9.44477. And that's the value that we compute. And if claim amount truly had no effect on settlement payment, the chance of obtaining a t statistic as extreme as 9.478 or negative 9.478 is almost zero. That's what it means, right? In simple terms, I repeat, if our claim amount had no effect on the settlement payment, really, then the chance of obtaining a t statistic that you see here as extreme as 9.478 or negative 9.478 is nearly zero, as you see. Since the probability is much smaller than this 5%, we reject the null hypothesis and conclude that the regression coefficient is statistically significant. All right, that's basically what it is about. Now, these asterisks are very interesting because it means to what probability your p-value is significant. Okay, for example, if you had only one star, it would mean that your p-value would be a significant at the 5% level of significance, but it would not be significant at the 1% or 0.1%, things like that. Okay, so if it is double star, it means that your p-value is significant at the 1% level of significance. But this one, given that it's 3 star, it is even beyond the 1% level of significance, which is 0.01%, 0.1%, sorry, level of significance. Okay. Now, the smaller it is, the more obviously the significant it is. And if it is a dot, if you got a dot here, it would have meant that your p-value is not significant at the 5% level of significance, but it would have been significant at the 10% level of significance. So it all depends on your analysis, what level of significance you are choosing as a given level of significance. Okay, then on that you will be able to interpret your output well. Okay, but generally we aim for this single asterisk. Okay, we aim for this single asterisk. Now there are other things that I want to discuss here, which are these output. Again, I'm explaining all these right now because if ever one day some of these information are hidden to you, you should be able to to compute them and determine them yourself. Okay, so for example, we have 8 degree of freedom. 8 degree of freedom is very simple to understand. If I come and I hide this information to you, it all depends on what we have been doing here. This is a degree of freedom. The degree of freedom in a t distribution for a regression analysis is n minus 2. So you just need to know what is the sample size and subtract 2. For us, we know that the sample size is 10. So we subtract 2, we get the 8 degree of freedom. So if in case but I do hide this information of 0.8, you should be able to know how to do it. And then you have the residual standard error. Now, what is this residual standard error? The residual standard error is 1.082. We've already been talking about that anyway. Uh, where is this? Here we go. It is the root of this 1.171. It is the square root of this 1.171. So that is the residual standard error. So if you want the residual standard error, you will need to be able to find what? Let me come back to this. You will you will need to find the square root of that thing here. All right. You will need to find the square root of this. Okay, you will need to find the square root of that. That will give you the residual standard error. We may give it a try and just check if you want to see if we got the same thing. Okay, we have 1.082. So are we really getting the 1.082? You would recall I've computed that earlier. So if you do SE, you will see that it is 1.082. So in that particular setting, you would need to know what the sum of squares of x is to be able to find 1.082. If the sum of squares of x and all this information are not given, generally I'm not going to give you that. But it all depends. If you have a small data, then you might have to add to compute it yourself, things like that. But at least you know how this is obtained. The residual standard error is just that component of the equation that I explained to you. And then you have multiple r squared, which is also of relevance. Now, I'm not going to discuss everything else, but I'm going to discuss mainly this one, the multiple r squared. The multiple r squared is this is what we refer to as a coefficient of determination, right? Coefficient of determination. This is what we call the multiple r squared. And we got a value of 0.9182. Right? What does this mean? First of all, how do we obtain that? To obtain that, it's very simple. You will need to take this. You need to have your correlation first of all. You remember in our previous exercise, we have computed correlation and it was 0.95824. 0.95824. This you have done in the first semester. So if you take 0.95824 and you square this value, you will see that you get this 0.9182. So this multiple r squared is obtained by squaring rather the correlation coefficient. Of course, we are referring to the Pearson product moment correlation coefficient here. Now, the question is, what does this mean? I think you already have an idea in the first semester, but I still mention it here just in case if I did not talk about it. So the multiple r squared here refers to is 0.982. 0.982 means 91.8%. I repeat, 91.8% of variation in settlement, that is in your dependent, is explained by claim. I repeat, this value of 0.981 means 91.8% of variation in settlement is explained by claim. your dependent is explained by the independent. So the higher it is, the better is X at predicting settlement. All right, that's the main point behind. The higher this value, the better it is at predicting performance. There we go. That was a little bit how we obtain these different values. So I repeat, sometimes in an exam setting, I can come and add even this information. But if I will add this information, I would expect you would be expected to have obtained some information elsewhere that will help you to determine it. If otherwise, I will not give it to you. All right. But there are things that I can come and hide in there, and you need to be able to know how to do that. If in case I give you a small data set and you have to find the, if I hide this information and you have to find it, you will need to find it yourself. Okay, so here we go. You will need to find it, and you know how to find it by using this formula that I explained. That's a little bit on regression. So to come back here in an exam setting, if in if I come and I give you this output here, if I give you this output as it is, and you have a t-value given to you, things like that, and all these different output, you have to be careful. Please do not repeat the calculation here. There is no need for you to do this computation. I repeat, there is no need for you to do this computation. You would just normally come and write t equal to 9.478. That's all you would have had to do. There's no need for us to do that as well. Because if this information is given, you put that directly. And then the only difference is that you will not write down if this, okay? Because you are using the p-value concept to conclude. So in my case, if p-value is less than 0.05, we reject H node. That's the way you would conclude. It's just a minor change to the conclusion. Since I'm not working in terms of critical value now, I will say since p-value equal to, since p-value equal to this, less than 0.05, we reject non-percent level of significance, etc. The same conclusion. So there's only a few amendments to do here. It's rather than computing the whole thing, you would rather put down the t-value. This is not 0 but 9.478. You would rather put the value directly 9.478, and you will mention that, and you conclude with regards to p-value. But you don't do both, please. Either one or the other. If you do the other, it's all fine, but the only thing that you have to do, if you've got an output like that, it's a waste of time for you to go. I repeat, if you've got an output like this, it's a waste of time for you to go and find the critical value when you can use the p-value directly. All right. So it all depends on what you have. And if you still do it, it's all fine. You will get your full marks normally if you done it well. But for information, if you have a p-value, it's far more appropriate to use a p-value unless um, there's unless some information are hidden that doesn't help you to do it. Okay. So here we go. That's how we can obtain the how we have obtained the regression output, and how we can do inference on regression based on this output. Okay, so by the way, you might have noticed that I did not discuss these. Indeed, I did not discuss these for one purpose, is that I'm not doing multiple linear regression with you. These results here mostly applies when we are working with multiple linear regression, but for us, that is not applicable here. So that's why I'm disregarding them for the time being. Thank you for your attention.